These are the notes on section 10.2, simplifying radicals. So our goal by the end is to solve a question like this. One application for simplifying radicals is using the Pythagorean theorem. Suppose you're bringing a mirror into your living room. What's the maximum height of a mirror that will fit through the doorway? So as we can see, if we just use the doorway here, well, we can only fit a mirror that's that tall. But if we use a mirror that goes kind of diagonally across the door frame, as shown with a dotted line, can be a lot higher. And one thing we can do to figure out that length is simplify radicals. A radical expression contains a radical. You might know it as a square root. It's called a square root because if there's no number there, that's the same thing as a 2. But the symbol is called a radical. This would be written and said out loud as 2 radical x plus 3. You might know or might have learned that the square root of x is the same thing as x to the 1/2 power. Again, that's because x has an exponent of 1, and anytime you have a square root, that has an exponent of 2 outside of the radical. So, if we were to write it, again, the exponent is always the top number, and the root or the radical is always the bottom. Characteristics of a radical are that the radicand, and the radicand means the number or the expression underneath the radical. So, again, radical expressions can't have perfect squares under the square root. So, for example, something like square root of 25, well, that's not actually a radical. That's the same thing as just 5. It's not simplified to say the square root of 25. A radicand can't have fractions, and no radicals will appear in the denominator of a fraction. So these all here show good examples of simplified radical expressions. You'll notice there's no perfect squares on the inside of the square root. There's no radicals in the denominator, right? And this radicand doesn't have any fractions underneath it. These ones aren't simplified. These are no good. These are not radical expressions that are simplified. So one thing to keep in mind when you're multiplying together square roots is this property. If a and b aren't 0, so if these numbers aren't 0, the square root of ab is the same thing as the square root of a times the square root of b. I think a better way to think about this that might make more sense is if you have the square root of 40, we could say that's the same thing as the square root of 4 times the square root of 10. Another way that might even be easier for us to think about that is this is the square root of 40, which is the square root of 4 times the square root of 10. So we could rewrite that as the square root of 4 times the square root of 10. And that's how multiplying works within square roots. We can use this to really help us simplify radicals. So, in my example right here, we know the square root of 4, well, that's the same thing as 2. The square root of 10, well, we can't really simplify that anymore. It's not a perfect square. But this would be the same thing as 2 square root of 10, 2 times the square root of 10. So that's what we'll learn next as a way to simplify from a square root that doesn't have anything outside of the radicand to a number in the front. Well, let's use an example. Well, we know 169, that's the same thing as 13 times 13. So we could say that the square root of 169, well, that's the same thing as the square root of 13 times 13. Well, we know that the square root of 13 times 13 is just going to be 13, and that makes sense because the square root of 169 is 13. But what about when we have square roots that aren't as even or aren't perfect squares? So let's say we had the square root of 200. There's a number of ways to do this, but one way I'm going to think about this is 200 is the square root of 50 times the square root of 4. 50 times 4 makes 200, the square root of 50 times the square root of 4. We all also know that the square root of 50 is the same thing as the square root of 25 times the square root of 2. So we could even rewrite this as saying this is the square root of 25 times the square root of 2 times the square root of 4. If we want to simplify this even further, we know the square root of 25 is 5 and the square root of 4 is 2. But there is no such thing as the square root of 2, so that would still, if we're simplifying, say the square root of 2. 5 times the square root of 2 times 2, well, that'll end up being 10 times the square root of 2. So we could write our answer as 10 square root of 2. I want to point out that there's a much faster way to get to this answer, and something that we should try to think about as we're solving all of these questions. I started by factoring this as 50 and 4, but what other numbers would have also resulted in 50 and 4? Well, 2 times 100, 10 times 20, there's all kinds of combinations. We want to try to think of the biggest perfect square. The biggest perfect square here is 102. The reason that's helpful is we can already simplify. Well, we know the square root of 100 is just going to be 10, and then that'll get us to our answer of 10 square root of 2. So just to kind of highlight here, if we, at the beginning, really try to think about what is the largest perfect square that's possible, it'll allow us to save time and effort. Either way, though, the square root of 200 is 10 square root 2. Another strategy that you can use is make a factor tree. So if we have the square root of 125 and we're not sure of the factors, well, we can just start breaking it down. 5 times 25 is the square root of 125. 25 breaks down into 5 times 5. This is called factoring or prime factoring the number. After I've prime factored the number, I'm going to look for pairs of numbers. So here I see there's 3 5s. So this is almost the same thing as the square root of 5 times 5 times 5. We know the square root of 5 times 5, well, that's going to become the square root of 25, or just 5. So if you see a pair of numbers, we can move that number to the outside. So if we had the square root of 125, that's the same thing as 5 square root of 5. That's an especially helpful strategy if you can't think of perfect squares, or if you have numbers that aren't easy to think about. So for example, with 68, we could always take 2 out of an even number, 2 times 34. We can always take 2 out of an even number, 2 times 17. So even if you didn't know at the beginning, 4 times 17 gets you to 68, well, you could figure out this is the square root of 2 times 2 times 17. This pair of 2's, the square root of 2's becomes just 2 on the outside, so our final answer is 2 square root of 17. And again, just to highlight that other strategy, for this one right here, if we think of the largest perfect square, well, that's 9 times 8. Well, could we think of something bigger? Well, yeah, 36 is a factor of 72. So if we think of that right off the bat, we know this is the square root of 36 times the square root of 2. We can quickly get to the answer, 6 square root of 2. Okay, but all of those are good strategies for simplifying radicals, for finding those perfect squares, or factoring all the way down. All right, so go ahead and take a second to copy any of those down that you didn't get so far.